So after I've extracted uranium, it is time to extract the only other radioactive element that is significantly present in the Earth's crust, and that is thorium. Thorium is mostly present in the minerals thorite and monazite, which are found across the world. But the prime ore for thorium is monazite and not thorite, despite their names. Not because it contains a huge amount of thorium, but because monazite is mined and processed for its rare earth content, of which thorium is a byproduct. Since rare earth elements are increasingly more popular, we're also seeing an increase in the production of thorium. And not because thorium is suddenly so popular. It is just a result of them being present in ore together. The use cases of thorium are still relatively small, despite the increasing production. It is therefore not something that brings in a lot of profit. It finds some use in optics, ceramics and alloys, and potentially in a currently unused type of nuclear reactor. And that's pretty much all there is to thorium. So this time I bought 2 monazite rocks, and they're also a lot heavier. Thorium accounts for only 5 to 20% of the rock's weight, in the form of thorium dioxide. The rest consists mainly of phosphates of lanthanides, such as cerium and lanthanum phosphate. Anyhow, before I check the radioactivity of the monazite, I do a background check. And the natural background radiation is only 10 CPM, which is only from beta and gamma particles, because this detector cannot measure alpha particles. Now I take both rocks and put the radiation detector directly on top of them. It seems the radioactivity is about 1600 CPM, which is not that bad compared to the uranium rock, though thorium decays through alpha decay, which the detector cannot measure. So we are not measuring any radiation from the direct decay of thorium, but only from its daughter nuclei, many of which are strong gamma ray emitters, which relatively quickly decay to form lead. There's also a very tiny bit of uranium present in this rock, which can also contribute to some of the radiation. Now let's take a closer look again, before they're torn apart into their components. They are both very hard orange-brown rocks, with a little bit of shine. They feel slightly waxy, and thorium minerals are often what is called metamict, which means that the crystal structure of the minerals is completely destroyed due to the alpha radiation that is let off from the decay of thorium, leaving the mineral completely amorphous. We can possibly also see another sign of radiation damage, which are pleochroic halos. These are tiny black halos of discoloration that are caused by alpha particles, often found around inclusions of radioactive crystals inside another mineral. But I'm not sure if that's what we're looking at, though they are known to appear in monazite. And that's pretty much all there is to it. These specimens aren't too exciting, compared to many other minerals, so we can destroy them with peace of mind. So I set up a large flask and drop in a stir bar, and both rocks, which have a combined weight of 38.17 grams. Now I add about 300 ml of a 75% sodium hydroxide solution. I then set it in a heating mantle and heat it to 150 C and wait for the rocks to get consumed. But it was really slow, because I didn't feel like crushing them and have radioactive dust spreading. And because I was heating a strongly basic solution for so long, with stirring, my flask broke and I had to move it all to a beaker. So this asks for another method. But first, I will recover whatever was consumed. I already took out the rocks and I diluted with some water and filter it all. Some hydroxides are left on the filter, along with glass particles, which I will set aside and add later. Now I first want to try a way to crush the rocks to a powder, without having it spread dust. My idea was to use a rock tumbler as a mini ball mill to crush the rocks. So I bought this beautiful kids rock tumbler that features very interesting text, such as kids can collect various kinds of rocks outdoor and wet them into extremely attractive, keen diamonds with the machine. Okay, so maybe my rocks will also turn into diamonds. So I put the rock remains in the tumbler, which only lost about 2 grams in weight. And with that, I put some small steel balls. So I put it on the machine and let it roll for a while. I also tried it with much larger steel balls. So I had to pull out the simple method, which I should have just done right away. So I put them in a bag and smashed it with a hammer. And then put all the remains in a flask. I add in a stir bar, and then a random amount of concentrated sulfuric acid, which is not able to eat glass. I heat it to 230 C and leave it to stir overnight. In this reaction, all the components are converted to their corresponding sulfates. After a while, it becomes grey, and the next day, it is a cream-colored sludge. I let it cool down to room temperature and then filter it all through. I keep adding water until all of the sulfates dissolve, and only the insolubles remain on the filter. Now to the filtrate, I gradually add 25% ammonia solution to bring the pH to a little above 1, which will cause the thorium to precipitate out as thorium hydroxide, along with a tiny bit of the rare earth hydroxides. I then filter it all through to collect it and dry it on the filter for a few minutes. I then scrape it all off and transfer it to a crystallizing dish. This part should contain all of the thorium, and we see it is mildly radioactive. I set it aside for a second and then return to the filtrate. I forgot to add it before, but I still have whatever I recovered from the first try with the sodium hydroxide. So I just add it all to the filtrate and also add a tiny bit of sulfuric acid to make sure it stays acidic enough to dissolve everything. What stays behind as a solid should all just be glass that was eaten away from the flask. I transfer most of it to a beaker and filter all of the contents through to get out all of the glass particles. First I washed out the flask and then filter all of the contents from the beaker through. It was very slow, but afterward all of the glass particles are gone. So now I transfer half of the glass pre-filtered to a beaker and again start adding in ammonia up to a pH of about 3, which will precipitate out all of the rare earth elements in their corresponding hydroxide. I do the same with the other half and then filter it all again. What is left behind is a jelly-like material, which are the wet rare earth hydroxides. Normally it should be washed with water as well to remove all of the ammonium sulfate, but I am not going to process this further and I will just store it for now. The filtrate is light yellow. It still contains a tiny bit of rare earth hydroxides and also uranium, but it is not worth recovering, since on this scale the amount of uranium is too small, so I simply discarded it. I moved the rare earth jelly to a crystallizing dish, and we can see that it doesn't have significant radioactivity. Anyhow, now returning to the thorium precipitate, it will have to be purified. So first I convert all of the components to their corresponding nitrate salt by boiling it in concentrated nitric acid. I occasionally add more nitric acid, and after a while it has turned yellow. A little while later, when it seemed to have all reacted, I transferred it to a flask and set up a separatory funnel. I wash out the dish with some water and then transfer all of the contents to the separatory funnel, and I wash out the flask with water as well. Now to extract the thorium nitrate, we need a suitable organic phase, which are generally long chain alkanes of around 12 carbons, such as dodecane. In this case, I will use a mixture called Shell Sol T, which is a synthetic mixture containing C11 to C12 alkanes, but something like kerosene can also be used. Then to be able to move a water-soluble salt into an organic solvent, I will need to complex it with something that is very non-polar, which is tributyl-phosphate. So in the same flask as before, I make a solution of 20% tributyl-phosphate in Shell Sol T, and then add it all to the funnel. Now originally I thought it was going to be a standard extraction, like we have seen many times before, but it is not really an extraction in that sense, and the wording kinda misled me. After doing some more research, I found out what should be done instead. I had to let the mixture stand for a while, and it got a little bit crusty, because the tributyl-phosphate also degrades slowly from the nitric acid. But it is important that there is nitric acid, otherwise the tributyl-phosphate reacts with water. Anyhow, I moved part of the mixture containing the thorium nitrate solution in nitric acid and the tributyl-phosphate solution in Shell Sol T to a beaker. I then added some more Shell Sol T and some more tributyl-phosphate and drop in a stir bar. I add as much as possible to the beaker, and I then leave this mixture to stir strongly for a day. And I do the same with the mixture I have remaining. In this very slow reaction, tributyl-phosphate reacts with thorium nitrate, forming a complex which can dissolve in the organic layer, and thus pulling it out of the water layer. When I come back the next day, it is a little bit more orange, and when I stop stirring, the layers separate normally. I then separate the layers in a separatory funnel, and take the upper organic layer, containing the tributyl-phosphate thorium nitrate complex. I move it to a beaker, and then add a bunch of water, and again stir it for a day. Now that there is no nitric acid, the tributyl-phosphate gives up the thorium nitrate, and complexes with water instead, while staying in the organic layer. The thorium nitrate is then moved back into the water layer. When I come back, I again stop stirring, and the layers separate normally again. Now I separate them again in the separatory funnel, and take the water layer containing the thorium nitrate. I have put it all into a flask, and just distilled off all of the water. When that is done, a white solid is left behind. But I probably did an oopsie here, by heating it too strongly. causing the thorium nitrate to decompose to thorium nitrate oxide or even thorium dioxide. Thorium nitrate also has quite a low melting point of 55 C. Anyhow, I just ignored that, so it didn't happen, and I removed the short path apparatus and added a bunch of concentrated hydrochloric acid. This should convert the thorium nitrate into thorium chloride, with the release of nitrogen dioxide. We see immediately some nitrogen dioxide is released, but it quickly disappears, after I added some more hydrochloric acid through the condenser, and it also doesn't produce any more. It also doesn't all dissolve, which should be expected from thorium nitrate, as well as thorium chloride. This makes me think that only a tiny bit of thorium nitrate survived. I let it boil overnight, and then again distill off all of the acid. A white solid is again left behind, which I hoped was thorium chloride, but it seemed to be thorium dioxide, since it didn't dissolve in water. Thorium dioxide can dissolve in acid, which is why over time it did dissolve. Oh well, it isn't too bad, since I didn't really plan on using it anyway. I moved all of the solid to a crystallizing dish, and the yield turned out to be 4.71 grams of presumably thorium dioxide. If we assume it is fully dry and it doesn't contain other lanthanides, the thorium content of the monazite would be 12%, which is on the higher end, since monazite typically contains about 6% of thorium dioxide. Now measuring the radiation, we see it only reaches about 280 CPM. This is because the uranium impurity and most of the daughter nuclei were removed. This leaves us with a less radioactive product, though over time, this powder will build up daughter nuclei again and become more radioactive. Anyhow, that was it. Subscribe for more radioactive chemistry. And as always, a special thanks to all my patrons. See ya.